Hello, everybody. Thank you very much, Duan, for the organization once again. I'm Rhushik MATROJA. I'm here to talk about how can we bring generative design to the concurrent engineering. We had some great talks yesterday and today. Being a relatively new kid on the street, on the block, could be intimidating, but it's inspiring to see that this whole shift that we can see from last year's CDFAM and this year, big challenges are coming up, and we have to get ready on it. At Cognitive Design Systems, we are very simple and pragmatic people. We think to believe so. And we want to solve a simple issue. We want to make parts which are performing, manufacturable, at least cost, and sustainable. And for that, we looked into how engineers are creating this kind of geometries, parts from end to end. And we end up finding that there used to be a concept in the European space field called concurrent engineering, where we create a small task force with design engineer, simulation engineer, manufacturing engineer. And the idea is to bring out the design, which is, or the part, as fast as possible. At Cognitive Design Systems, just a little bit introduction, we are a small bunch of people in south of France, Toulouse, beautiful place, if you have ever visited. We work a lot with European and Japanese customers, and yeah, we are about 4.5 years old. Our vision is quite ambitious. We want to transform engineering into cognitive creation. When I say cognitive creation, it also involves on how to make a process which is fluid, which is very easy to use, engineering making it more easier, but also not doing again and again same processes. Making the engineering process that has been already done in the past, reuse it in a way that it can be leveraged in the best way possible. And for that, we want to break the silos. I see that a lot of companies presented just before us have also that ambition, and we are all in for that together. We want to accelerate the sustainable design. That's a maybe very European thing to say, but that's a very important thing, and I truly believe that it has to be focused, which is a little bit shifting right now, but it has to be focus of engineers of tomorrow. And we want to automate the innovation in the right way by using the AI, but in the right way to make it useful. For that, we are relying on our technology enablers. So we developed our own implicit modeling kernel, which allows us enough flexibility to modify the geometry, optimize the geometry in the best way possible. We combined it with data-driven design decision algorithms. So we do manufacturability analysis, we do cost analysis, we do carbon footprint analysis, and we couple it with our optimization solvers so we can improve the whole design much better. And at the end, we have our UI and UX, which is very user-friendly, where we are able to create a reusable engineering workflows, and we can iterate faster. And by doing that, the whole idea is to create a accelerated, scalable, intelligent engineering. That was not the real idea of creating any assumptions on Illuminati, but it looked like that a little bit. So how we are bringing concurrent engineering to our workflows. So for the concurrent engineering, we start with engineers first. So engineers who want to start from some specifications, could be functional regions, could be what kind of material, what kind of cost we want to achieve, and we end up creating the best possible. On top of that, that know-how that engineer has created could be used by the engineering team. It could be different engineers from manufacturing side, from simulation side, and they can collaborate on the same product, on the same project in the best way possible. And at the end, this whole workflow has to be captured as an engineering know-how by the organization, so they can reuse those engineering intelligence for other purposes, for same family of paths, for example, and in order to accelerate the whole product development cycle. So to do that, first of all, we started creating our own algorithms. I will talk a little bit more about it. Of course, topology optimization has been talked quite a lot, but we believe that topology optimization serves pretty good in certain specific fields, but not for all use cases. So we started creating new use cases, specific optimization algorithms. So I will present it a little bit in later how we do that. Design exploration, that is also something that has been focused today from Altair, from Antop, from Synera also. That is also very, very key, but our approach is to make sure that each design that has been generated is manufacturable. We know the cost, we know the carbon footprint of it, and in that way, we can take the best decision while selecting the design. And at the end, of course, our core pillar is the design for manufacturing. Assessing the manufacturability early on in the design cycle is very important to make sure that we don't bring out some artworks. And nothing against the artwork, but if the part is not manufacturable, what's the point of the design? So making sure of that is our key priority. And by doing this, we create our engineering database. So here is the first optimization algorithm, topology weaving. It's a name that we gave it. I'm open to discuss about how can we name it better. It's simple. We wanted to connect functional regions between them in a confined region, like topology optimization, but we wanted to make sure that it's completely parametric. So we can reuse, we can modify geometries locally, or we can modify those parameters to refine or fine-tune the algorithm. So what we did is that we connected it with a manufacturing analysis solver, we connected it with a stress solver, and we assess that, okay, what's the best way to connect those functional regions? So we have simple connections, but then we assess that, okay, the stress is there. So let's modify it, and we modify the geometry accordingly, and it goes through there. And it all splines, it could be splines, it could be surfaces, so you can come and modify also those geometries much better. And you have full flexibility. A small example just under the same part that we designed with different design intents. One in additive manufacturing, another one in die casting, another one in machining. And you can see that the results have been come out of the same algorithm, but as it has been driven by the manufacturing insights, the design is completely different. I don't know if it's visible. Yeah, there you go. Another algorithm is generative enclosure. Something that was missing in topology optimization was that we can't create all the time watertight geometries. And those watertight geometries, because inherently topology optimization will create some generative design which has a lot of holes, looks beautiful. But if you have to put some oil in it, you have to put some other stuff, it's not possible. So this algorithm was very simple. We bring in the functional regions as it is, and it will automatically create a surface which connects all the functional regions with the same thickness. And this allows to create very fast a first geometry that you can iterate with simulation-driven design. So you can modify the thickness, you can add ribs, you can add stiffening elements to make it more performing. On same time, keep the manufacturability in check. all these different algorithms, of course, we have also topology optimization, but I'm not presenting it because it's already has been discussed quite a lot. We can generate lots of different concepts. And this concept has to be analyzed and validated. And for that, we have our Design Explorer, where you can actually map out all the concepts that has been generated. You can compare cost, carbon footprint, you can compare different performance level, you can compare also various different kind of KPIs, and select the best part which is suitable for your specific requirements from the very beginning. And this could be done completely automatically and could be reused. So let's talk about the manufacturing-driven design. So manufacturing-driven design, we select, first of all, the process that we want to manufacture with. Could be die casting, molding, machining, additive manufacturing, other processes. We assess the feasibility of it. So we have our algorithms which allows you to assess where the risk with the manufacturing is. And then we have some other algorithms which automatically modifies the geometry to make it more manufacturable. Very simple, but effective. And that could be done very fast with full control from the user. And all these workflows has to be done in a way that it's reusable. So we can create reusable workflow. I'm not sure we can see it very well, but yeah, you can take one part, one design space, you can optimize it, you used it for project A. Now, this workflow has been created, it could be more or less complex. You can give it to your colleague who has some different requirements. He can also bring in another part, which is completely different, but he can reselect the functional regions and apply the loads and regenerate the model very fast. And this reusability of sharing those workflows with or without the 3D models inside is very important, and that's what we see at our customer level, that they are reusing it fantastically. First example here from the aerospace industry is the aircraft door bracket from Thales. It's a supplier of Dassault Aviation. Of course, France, Toulouse, we turn around those people very quickly. Idea was that, okay, we have a concept here. We want to create the new door for the Falcon 6X that is coming. What is the right way to manufacture this part? So let's explore design for manufacturing, so for 5-axis machining or for additive manufacturing. And by doing that, we can know that, okay, the whole exploration time, which was reduced dramatically, we were always aware of the cost and the manufacturability of those components, which was a real advantage here. And we were able to bring out the most optimized part, which was 5X machining and not the additive manufacturing, because of course the cost was not same. And it was displayed at Bourget last month. Another example from the new space industry, from T4I, it's a satellite propulsion manufacturer. They wanted to create this fuel tank, pressurized satellite tank, fuel tank, and they wanted to explore the possibilities of what they can do. 150 different lattice variants that they used internally were analyzed in half day or a little bit more than a day. And at the end, we found the right one, which has the best performing criteria, which was relatively easy to manufacture, and which was also what they were looking for. The stiffness level was the best. All this, now we are talking about our research part, which is coming by the end of this year. My CTO is here, he can confirm it. We are working on the multidisciplinary optimization. That makes a lot of sense because we want to automate the optimization for cost, for carbon footprint, and it has to be done automatically also. The user can always have the parameters that he can fine tune, but we also want to accelerate that. by using surrogate modeling and by using our homegrown optimization algorithms. And the last point that I want to discuss is also something that has been a bottleneck for the industry, which is conversion of, because all these implicit models and mesh models, they're great, but we had to bring it back to the CAD because 99% of the people, and I'm sure people from the Dassault system here can confirm, that if we can't bring it back to the CAD, we can't bring it back to the PLM in the right way, and that could be a problem. So we are spending a lot of time doing mesh to CAD conversion, automatically, of course, with the minimal user intervention. We use the mesh, recognition of different features, so primitive features, cylinders, flat surfaces, torus, etc., etc. We recognize it on the mesh, and then we recreate the BREP geometries, so we can bring it back. We can reuse the parametric 3D model. Of course, if the surfaces are curved or anything, that remains in the patches, like we can see here, but the functional regions becomes much more cleaner. This is it's a kind of a little bit complicated to explain on this part, but yeah, if you have very simple parts, that can be perfectly converted to the CAD. The beta will be released end of this year, and yeah, if you are interested in it, you can come to talk to me and my colleague at any time. Thank you very much for your time.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.